Great, thanks for inviting me. It's very nice to be here. This might be the first classroom in Princeton I was ever in, so it's nice to be back. When I was here, Robert Gunning was at the front in a bow tie saying something, so I guess I'm not as elegantly dressed as at that time. So I'm excited to tell you about some joint work with Kristen Hendricks on computing involutive Heegaard Floer homology. So I'll start by telling you what involutive Heegaard Floer homology is. It's a variant of Heegaard Floer homology introduced by Kristen and Hendricks-Manolescu in 2015. Then I'm going to tell you something about the technique when you use the computer, which is bordered Heegaard Floer homology, which I guess is being taught in the summer school at the moment with some part happening on Monday. So after Monday, you'll understand part 2 of the talk. And then I'll tell you how to use 2 to compute 1. So, Heegaard Floer homology which is a locally grown family of 3-manifold invariants due to Peter and Zoltan from roughly 2000. Well, it does lots of things. So one thing it does is to a closed, connected, oriented 3-manifold, it gives you some graded abelian group. Maybe I'll work with F2 coefficients everywhere. So a graded F2 vector space called HFhat and a graded F2 brackets U module called HF minus. Various other things. So let's see some properties of these. These are functorial with respect to covariatisms of 3-manifolds, so smooth covariatisms. Why are they called Floer homology? Well, it's the homology of some chain complex, so homology of chain complexes CF hat of y, CF minus of y. Right? Single out a few other properties. So if you take a connect sum, CF hat of y1 connect sum y2 is CF hat of y1 tensor CF hat of y2. What else do I want to say? They decompose according to spin C structures on Y. So if this is, maybe I'll say graded by isotopy classes of non-vanishing vector fields. On Y, so CF hat Y is a direct sum over vector fields V, isotopy class of vector fields V of CF hat of Y V. Now there's a Z action on the set of non-vanishing vector fields, on the set of isotopy class of non-vanishing vector fields, because the non-vanishing vector fields in S3 is in bijection with Z via the Hopf invariant. It's an exercise. And that gives you a relative Z grading, that's the homological grading here, and then the orbits give you another decomposition into spin C structures. Okay. I should mention this is this fact is due to, or this reformulation is due to Grip and Huang. What else did I want to say? Has lots of applications. Some will be given in future talks, and some will probably be given in the summer school, and essentially none will be given in this talk. It's defined via some combinatorial way of representing the three manifolds, so Heegaard diagrams. So here's a not very interesting one. I think blue was a little hard to see in the back, so let's go with green. Okay, that's it. So, okay, that was Heegaard Floer homology. So, involutive Heegaard Floer homology. Is due to Hendricks-Manolescu. Well, there's a Z2 action. So this is okay. So this is a partial analog of Manolescu's pin 2 equivariant Seiberg-Witten Floer homology. Which was also developed extensively with a different definition by Francesco Lin. So one version of the idea is, well, there's a Z2 action on the set of non-vanishing vector fields given by, well, just sending a vector field v to minus v. Okay. And this is reflected, so this has a lift to Heegaard Floer homology. So what you do is you take your Heegaard diagram H, and now I get a new diagram which I'm going to call minus H beta. So what you do is you reflect the diagram or reverse the orientation on the Heegaard surface, and you exchange the roles of alpha and beta. So this is the hard part of the talk. This is the very hard part of the talk. Okay, good. Nope. Fail. Okay, maybe. Okay. These represent the same three manifold. So these both represent same three manifold. Gesundheit. Now I get, there are two isomorphisms. I want to give them names. Yes. So there are two isomorphisms from any version of the Floer chain complex of, or two, I should say, homotopy equivalences. Homotopy equivalences from any version of the Floer chain complex of the diagram to that version of the chain complex for my new diagram, minus h beta. So let me call these maybe capital phi and capital C. So one of them is the sort of obvious map. So if you take a generator here, a generator for the Floer complex here is a pair of points in sigma, and you just apply the reflection of that pair of points. You get a pair of points over here. Okay. So that's the map, maybe phi. Okay, so my map phi. Okay, but also you have a map. So since that was phi, and then the second one is since h and minus h beta both represent the same 3-manifold, you can get from h beta minus h beta rather by a sequence of Heegaard moves. And that gives you the map. So the invariance proof, the Ozsváth's invariance proof, gives you another map, C, from FH to CF of minus h beta. One reason I drew a nominally complicated diagram is that I wanted to point out that it's not that the two diagrams are diffeomorphic. For example, on the left, there's an alpha circle that intersects only one beta circle. It intersects it once. But on the right, there's no alpha circle that intersects one beta circle once. Each alpha circle has more than one intersection point on it. So the diagrams are not diffeomorphic. You have to do some moves to get between them, but there are moves that get you between them. Okay. Fine. So now I have two isomorphisms or homotopic equivalences between these complexes. So this gives me a map iota from CF of H to itself by just composing one with the inverse of the other. So let's say phi inverse composed with psi. You can show that iota squared is homotopic to the identity map. Great. Sad. And then, so let's say CFI minus of y. You look at the mapping cone of the map iota. So, sorry, 1 plus iota. So i.e. you take, this is CF minus of H plus CF minus of H with the differential, okay, is some matrix, right? So the differential is the differential on CF minus, and this map 1 plus iota as the diagonal term. Okay. And similarly, CFI hat, where you replace all the minuses with hats. Okay. And then again, Hendricks-Manolescu show that up to isomorphism, these HFI minus HFI hat are invariants of Y. And they get various applications. There have been a number of other applications, since mostly the problems about homology cobordism. All the applications use CFI minus. So some applications, so exist various applications using this CFI minus. For this, I think I need to work over mod 2 coefficients, or at least they've only done it over mod 2 coefficients. Francesco is maybe here. Yes. What about in Zyberg-Witten? In Zyberg-Witten, you could do this over Z, right? Okay, so it's an artifact of the fact that if you want the sort of naturality, there's an up to sign issue, I guess, if you're working over Z that's not being understood as well here as in Zyberg-Witten. This is supposed to be imitating Z2 equivariant homology in the sense of Borel, and that's, you wouldn't want to Q or mod P for another equal to 2 because it sort of collapses to be uninteresting, but there is some information over Z. Great. Other questions? I guess I have a couple of questions. As an aside, open questions. Sort of structural questions about this thing. So Zoltan brought up 1. So can you lift to Z coefficients? Again, I'm pretty sure they didn't do that. Another one is HFI, I don't know, minus an invariant up to canonical isomorphism. That if I have two Heegaard diagrams, I do moves between them. If I choose those moves differently, do I get different isomorphisms on HFI minus? For HF minus, you don't. It's well-defined canonical isomorphism. For this is not known. That's what you would need. That's something you would need to have well-defined maps associated with cobordisms, because that just means you have a well-defined map for the identity cobordism. If you don't have that, it's kind of hard to have a well-defined map for any cobordism. Okay. 3. Really, you're supposed to, what we should be doing is we should have our equivariant complex should look like, do minus still. And what Hendricks and Manolescu have done is they've just sort of truncated here. So they've taken just the first 2 columns. The problem is that iota squared equal the identity. It's homotopic the identity. So, you would need to put in sort of some information about the homotopies and so on to get a chain complex here. So the question is there a well-defined chain complex that extends it that looks like actual equivariant Floer, actual equivariant homology? So this should be to recapture pin equivariant Zyberg-Witten. Okay. That's great. So as I said, all of the applications so far use this invariant CFI minus. I'm now going to talk about the simpler thing, which is CFI hat. Okay, so the rest of the talk how to compute CFI hat. That's a good question. The question is, does the truncation correspond to homology? And not that you can do this, but I'm not aware of something people have looked at for any reason. Yeah, that's a good question. There's a spectral sequence there's a spectral sequence converging to equivariant cohomology by looking at over RP infinity of the Borel construction. And this is like looking at the E2 page of that spectral sequence. Yeah, great. So where am I? Here. So, so this is via bordered Heegaard Floer homology. Joint with Peter and Dylan Thurston. So I should tell you something about bordered Heegaard Floer homology. So this is an extension of Heegaard Floer homology to three manifolds with boundary. And what it does, so the structure is to a closed, oriented, connected surface. There's some associated algebra, A of F. So this is a algebra over F2. So this is, in fact, it's better than that. It's a differential graded algebra. So it has a differential. Okay. For example, for the case of the two-sphere, the algebra associated to S2 is just F2. For the torus, the algebra associated to the torus has a nice description as a path algebra with relations. So I'll write it this way: row 1, row 2, row 3, mod row 2, row 1, and row 3, row 2 are 0. We call this names iota 0 and iota 1. So here, for example, iota 0, this vertex corresponds to a generator of the algebra, and it squares to itself. And then other generators are paths. So for example, there's a path row 1, row 2, where you go along row 2 and back, along row 1 and back along row 2, etc. It's 8-dimensional. Okay. I didn't want to erase that. Let's keep that. So that was from earlier. Let's remember that. What else I want to tell you all? Oh yeah, maybe I'll say one. For the surface of genus 2, so surface of genus 2, the algebra, well, it has a non-trivial differential. The previous two examples don't, and the homology is 98-dimensional. Actually, it depends on a way of describing the surface. So there's sort of it depends on a handle decomposition for the surface. And this is for a particular handle decomposition, which I apparently can't draw today. Good. Okay. If you have a cobordism between surfaces now, y from F1 to F2, you get a bimodule which I'll call CFdA of y over A of F1, A of F, how do I want to do it? A of F1 and A of F2. Okay. It's a differential graded bimodule, just like we had a differential graded algebra. So these come from a version of Heegaard diagrams. Here it is. So I feel like I should draw one. So for example, here's a Heegaard diagram for an elementary cobordism from a surface of genus 2 to a surface of genus 1. So it's probably drawable. So you take a surface of genus 2 and you fill in a thickened disk somewhere. The cobordism from surface of genus 2 to surface of genus 1. All right. These things are well defined up to homotopy equivalence. And if you compose cobordisms, you compose bimodules. So the way you compose bimodules is by tensoring them together. So if you have one surface and another surface, let's say it's y1, and then third surface, another cobordism to there, then CF dA hat of the composition y2 composed with y1 is CF dA hat of y1 tensor with CF dA hat of y1 over y2 over the algebra associated to, let's say this is F1, F2, and F3, the algebra associated to F2. Okay. Some special cases. So far this seems, I mean, there's no relation to the homology. haven't told you relation to Heegaard Floer homology yet. So if Y is closed, then you can make Y into a cobordism just by deleting two 3 balls, right? And you can consider CFDA of that. What's this an algebra over? Well, it's a bimodule over the algebra associated to the sphere, which is just F2. Okay, so F2 bimodule, that's just the same as a chain complex. I mean, a differential F2 bimodule is the same as a chain complex. So this is, in fact, just CFhat of Y. So in particular, by that theorem, I guess we call that the pairing theorem. By that theorem, you can take Y and you can cut it into pieces. And by tensoring together the bimodules of the pieces, you can reconstruct CFhat of Y. Okay. We're getting there. Good. The D is sort of representing the left boundary and the A is the right boundary. So if F1 is S2, I'm going to write CF dA of Y as just CFA of Y. And if F2 is S2, I'm going to write CFDA of Y as CFD of Y. Oops, I already wrote on this, right? Right. The last sort of general bordered thing I'm going to need is a particular diagram. So there's a miraculous diagram. AZ. Depends on which surface you're talking about. So it's AZ of F. And I'll draw it for the case of the torus. So not the straightest picture I've ever drawn. Okay. Fine. Green and red. Red, green. Okay. So there's this miraculous diagram AZ, and it has two great properties for us. One is, given a diagram H for 3-manifold with boundary F disjoint union S2. That's an example of one of those over here. So this is some diagram H. One thing you can do to H is you can mirror it and exchange alpha and beta. I can probably do that. This is no longer a bordered Heegaard diagram. So my bordered Heegaard diagrams, I had alphas going out to the left side. So I would like to say that this and that represent the same manifold, but this has red arcs and this has green arcs, so they can't. Okay. But what I can do is I can glue it to the diagram I had there. So let's try. Okay. So this is the analog of the operation we did in involutive Floer homology. I took minus h beta, and here I've also glued it to this diagram AZ. Okay. These both represent y. So h and minus h beta glued to AZ represent the same cobordism. And the second thing that's great about this AZ is that the bimodule associated to it is just the algebra as a bimodule over itself. So a corollary of these properties is that if I'm interested in CF hat of something decomposed into two pieces, that's just the chain complex of maps from CF d hat of y1 to CF d hat of y2. Okay. Crash. Okay, that was bordered Floer homology background. Now it's going to be new stuff again, so Peter should wake up. What are A and D? A stands for algebra and D stands for, say it again? AZ stands for Aru and Zarev. But there's no reason you should know that. But so this diagram appeared independent, so in papers of, so discovered by Denis Aru and Rumen Zarev. You guys know the story about how Banach spaces came to be called Banach spaces? So Banach wrote a book, and he said, we'll call these spaces of type B. And he puts a footnote that says, these type of spaces were first studied in the following paper of B. Banach, or whatever, Banach. And then he has a few chapters later, he says, recall a space of type B, and he says a footnote that says, see the footnote to the chapter previously, just in case you missed it. I think if you look on MathSciNet for what name, mathematics name, has the most citations, I believe it's Banach. So, okay. They didn't call them AZ. Yeah, it's a good point. Yeah. Okay, so so description of this involution iota from CF hat of y to CF hat of y using bordered Floer. So write y as a union of two handle bodies. Just put a minus sign somewhere just for the hell of it. Minus h2. So glued along the boundary, which is, say, f. So we have CF hat of y. This is, by that previous theorem, the complex of morphisms from CF d hat of h1 to CF d hat of h2. I can also consider the complex of morphisms from CF d hat of h1 tensor CF dA of AZ to CF d hat of h2 tensor CF dA of AZ. And there are two maps here. Let's call them phi and psi, abusing notation. So let me tell you the two maps. So one of the maps is, if I've got an element f in here, right? An element is a morphism from this module to that module, then I get a morphism from this module tensor AZ to this module tensor AZ just by tensoring it with the identity of CFDA of AZ. So right from here to identity, tensoring with the identity. Okay, so that's the map phi. The other map is, well, Gesundheit. I just told you that these, so psi, I better write it on the board. CFD hat of H1 tensor CFDA of AZ. This is the same as CFD hat of H1, let's say minus H1 beta, glued with AZ. And that's just the same as CFD hat of H1. So this is because they both represent the same three-manifold. They both represent the same cogridism. Okay. And similarly, CFD hat of H2 tensor AZ is the same as CFD hat of H2. Well, I'm taking the morphisms between these two modules versus the morphisms between two modules that are the same as them, that are homotopy equivalent to them. So there's an identification from the fact that I'm actually taking more of the same thing. So psi is induced by these isomorphisms, these homotopy equivalences. In other words, if I have a map from H1 to H2, what you could do is, well, you take, I now want a map from H1 tensor AZ to H2 tensor AZ. H1 tensor AZ is the same as H1, which maps to H2, which is the same as that. So the map is like there, there, and there. Okay, so this is psi. Psi of F, where this was F. So sort of nothing happens in either of these two maps. One of them you just tensor with the identity, and the other one you use the fact that the left side was the same as the right. Each of the pieces of the left side was the same as each of the pieces of the right side. And so the theorem that squiggle is hiding some Heegaard moves. So Peter has proved the following theorem. Iota is the same. And the proof is, you just check with Hagar diagrams that these are all the same description, where one of them, phi, is doing something like the reflection and take the same generator, and psi is doing a sequence of Hagar moves that gets you back to the original diagram. So this is not so hard. Not terribly hard. Okay, 10 minutes. Peter can now tune out again. Why does this let you compare HFI hat? Well, we need three things. Three-ish things. One, I need to be able to compute CFD hat of H2. And I guess CFDA hat of AZ. The second thing I need to do is I need to be able to compute, maybe I only need two things. Okay, let's say two things. Second thing I need to be able to do is I need to be able to compute capital psi. But if the map phi, I've just told you how you compute it. You take your element here and you tensor the identity element there. So there's no work to do to compute phi. But psi, I need to tell you how to compute. I'm going to tell you them in reverse order. One was done in earlier work with Peter and Dylan on computing HFhat by factoring mapping classes. I'll say something about two. So the point here is that CFD hat of H, this is a handle body, has no non-trivial graded automorphisms. So it's sort of rigid in some sense. This is an analog of something from Kovanov homology that was used to prove functoriality there. And that implies that there's a unique up to homotopy, homotopy equivalence from CFD of H1 to CFD of So there's homotopy equivalence like on the top board. Because if you had more than one, you can predict. I mean, these are, whatever, exercise. So how do you compute the thing? You look through all the maps, you find the homotopy equivalence, and you're done. In fact, if you look through all the graded maps, there's only one non-zero graded map, and that's the right map. Okay? I didn't want to do that. Oh. One. The tricky part about one, so I just need to compute CFD hat of a handle body. Okay? But the problem is that there are lots of handle bodies. So, so the difficulty CFD hat of H, so H is a cobordism. That means it's a three-manifold in our case, it's just a handle body, but in general, it's a cobordism, where the boundary's been identified with reference surfaces. Okay. Cobordism, you can go back and look at Milner's lecture on the H-cobordism theorem or something. Very classical. Cobordism is a manifold with its boundary identified. Manifold. You need that in order to be able to compose them, to know how to glue them together. So you want to form some sort of category. Objects here, services, more than cobordisms. So there are lots of handle bodies of genus G. Okay. How to compute? You just compute it for one of them, one simple one, and then you compute this bimodule CFDA for generators of the mapping class group, so for mapping cylinders of generators of the mapping class group. Actually, we use some groupoid version of the mapping class group that has a nicer generating set. Okay, and this works. So a few words about that, and then one more question. So so this works. There's a computer implementation where you give it your three-manifold. You have to tell it your three-manifold forms, and So the best version is due to Bohua-Jean. Uses this algorithm and some improvements of this algorithm due to him. And it's called BFH Python. And it's on GitHub. You can all go and look. It's manifold, and it gives you the HFhat. Okay. How do you type? Yeah, so there are various ways. One way is you can give into arc slides, or it'll take Dane twists, I think. Another way is if your three manifold was a branch double cover of a knot, you just give it your knot written down as a closure of braid, and it computes the Floer homology of the branch double cover. Or Platt closure of a braid, I guess is even better. Yeah. I don't think it doesn't take Kirby diagrams, though in principle, of course, you could turn a Kirby diagram into a Heegaard splitting, in fact, of monodromy, but it doesn't take them directly. And we extended to compute HFI hat, and then we computed for all remaining sort of branch double covers of K for K a knot with less than or equal to 10 crossings. Okay, that sounds great. There were 4 new cases. So it's not quite as exciting as that. Let me tell you the answer and the conjecture. So so K, I'm going to tell you the determinant of K, dimension of HFhat of sigma of K, and the dimension of HFI hat of sigma of K. Okay, so 10, 139, 10, 145, 10, 152, 10, 153, 10, 154, and 10, 161. 3, 5, 6, 3, 5, 6. Great. 11, 13, 14, 1, 5, 6. 15, 16, 5, 7, 8. Okay. These were computed by Manolescu. Also using a more conceptual way in terms of the branch double cover. These are Montesinos knots. The branch double covers are Seifert fibered spaces, and they computed it that way. You might notice our computation agrees with theirs. Okay, that's reassuring. You might notice a pattern here. There's some relation between these numbers, right? So we actually don't know if that always happens. So question. Is HFI hat of Y isomorphic to HF hat of Y plus F2 to the number of, let's say for Y, a rational homology sphere, the number of spin structures on Y, which in each of these is 1. I think that's, in all known examples, that's true, but there are not so many known examples, so I'm not sure whether it's true or not. Okay, I'll stop there. Conjecture, you mean this question? I don't know. Kristen would know. It's known for some classes. Maybe it's known for ciphered fibered, but I'm not sure about general graph manifolds. Francesco, do you know? No? That's a good question. That's a good question that I don't know the answer to. I mean, so did they computed for that? Yeah. For the examples they computed for, Kristen tells me that this is true, but I'm not sure if it means for the whole family. Email Kristen; she'll tell you. Yeah. Good. Sorry. You should also email Kristen. No. What's the question first? Then I won't answer it. Yeah, that's a good question. Yeah, so Boha did a bunch of things. One is he wrote this program. Another thing is he gave a computed proof, but with no holomorphic curves, entirely combinatorial, that HFhat is a three-manifold invariant. You could try to do that phi hat. That's my guess. It's tractable. We didn't try. Somebody could do that. So that might be an interesting project for somebody to do, is to just give a proof directly this is a three-manifold invariant. Another thing you can do is you can define what was the structure we needed in order to make this work. Was we needed this isomorphism. And you could define the bordered involutive Floer homology to be a bordered module, the invariant of y, together with this isomorphism. And there's a natural sense in which you could expect that to be an invariant. I mean, it's like, if you think about what should it mean for a thing with an isomorphism to be an invariant, there's a natural guess, and we conjecture that's an invariant, but we haven't proved that. That needs a little bit more naturality for bordered Floer homology than we know. So that's another question somebody could do, and maybe somebody could do that combinatorially also.
That's a question about arbitrary homology.
Oh, that's a good, so I like that comment. So Matt points out, for branch double covers, there's also an involution on the three-manifold. And so that gives you an involution on HFhat, but looks sort of like iota. It does, I think, the same thing on spin C structures. That needs checking. I don't bet my life on that. That's not this involution. Those are different. So you can give examples of branch double covers that are homeomorphic, but where the involution on HFhat, so two different knots with homeomorphic branch double covers where the involution on HFhat is different for the two different knots. So this question, I guess, in general, I don't think that extra involution helps you, but I don't know if it's false in general. It's not a, I didn't say conjecture. I don't think it's true. I like it too. Yeah, what about a spectral sequence from, so Francesco has a paper giving a spectral sequence from a variant of Gavanov homology to involutive monopole Floer homology of the branch double cover. You could try to capture that in bordered Floer homology. I don't think anybody has seriously tried. It's a little bit tricky. One application of this is you get a surgery exact triangle for involutive HFhat, which was not known before. Francesco proved that for pin 2 equivariant monopole Floer homology. But somehow, because of the diagrams changing, it's a little bit hard to do things with these spectral sequences. Maybe you could prove it using these techniques, but that's not been done. Okay, Peter. Yeah, for surgery track triangle, we do by looking at this for the exterior of the knot, and then looking at the three ways of filling it in and just writing down maps. You have to write down maps and homotopies that commute with the involution. It's a little bit like some checking, but it's like a page or two. Yeah, that's right. What if you go up to 11? Yeah, my guess is that's a great question, or 12. Ozsváth's program is extremely fast. There's some important conceptual improvements in his thing that I didn't explain, and so it computes these 10 crossing knots. It computes the Floer homology, like instantly, a second or something. This ran sometimes, for some of these it took an hour and a half or something, and a little bit of as is slower. It will probably not die for 12 crossing knots, at least for most of them if you mess around, but it would take long to just run through the whole table, so we didn't do it. I mean, 11 crossing. It seemed like it would take us too long to run through the whole table, so we didn't do that. And 12 is pretty impossible. Yeah, I know. Yeah, I agree. We didn't do that. It involves some fighting with the computer to get it to. You see, why fighting? What does it do? It's taking a bridge diagram for the knot. So you have some plaits and then a braid and some plaits. And then you cut that into two pieces, and you can choose where you cut into two pieces, because anywhere you slice in the middle, you've got handle bodies on each side. You take the branch layer. So you choose where to cut it into two pieces, and then you run the algorithm I said. You do the thing that I said here. Okay. And for these knots, if you cut it in one place, you could get it to compute, and if you cut it anywhere else, the program on my computer ran out of memory and crashed. So it involved sort of fiddling around a little bit for each knot to get the computation to run just by choosing where to cut, and I got lazy. Somebody should do that. I agree. I like surgeries too, but not as much as I like the spectral sequence from Bonabanach. That's a good question. Can you use this to yeah, so for example, for involutive Floer homology, there is currently a large surgery formula for HF minus and HF hat. And there's not a formula for arbitrary integer irrational surgeries. It probably is possible to use this technique to prove a surgery theorem for arbitrary surgeries for HFI hat. But it hasn't been, I mean, somebody could do that. That hasn't been done. If somebody does that, they should send me an email so that I don't suggest it to somebody else. But this technique probably would apply to help you compute for surgeries, but that hasn't been done. Somebody is not yet doing it, but I'm sure somebody will. Yeah, what about the minus version? Well, that would need somebody to finish writing a construction of bordered Floer homology for bordered HF minus, and I believe there are people working on that, possibly during this talk. But it's not going to be done by the end of the conference. That's right.